Hello, everyone, and welcome to the second fundamental theorem of calculus. So, in a nutshell, the first fundamental theorem of calculus says that if you are looking for the definite integral for a function small f of x over a b, if you happen to have a primitive, let's call it big F, over that interval, then the value of the definite integral of that function small f over ab is the output of big F at b minus big F at a. And again, the true power of the first fundamental theorem of calculus lies within the fact that we have a primitive. But now the true question is there a primitive out there? And the answer is yes, thanks to the second fundamental theorem of calculus. In order to present the second fundamental theorem of calculus, we need first a definition. Let small f of x be a function over interval ab, and let c be a number inside the interval ab. The accumulation function, also known as the surface function, I prefer to call it the surface function because we're going to compute areas of surfaces, but the real terminology is accumulation function, is a new function that we're going to call big F of x. And that big F of x is going to compute the definite integral from c, so c is fixed, chosen within the interval, to x. So here, be very careful. The variable for big F, the new surface function, is the upper bound of your definite integral. And then the original function, where we're computing areas under that curve, small f, its variable is going to be t. So we don't want like a confusion between the new function being big F of x, so the area between c and x, and the function itself, the small function that we're using, small f, so we're going to use t. T is also known sometimes as the dummy variable, but I don't know why they call it that way. So of course, this big F is going to be well defined as long as x is a number within the interval. Two remarks for the surface function. First, because small f is integrable, then big F is well defined in the sense that you can compute it and it's always going to give you a unique value. But of course, maybe the way you're going to compute that output is going to be through suffering, maybe by computing the limit of a Riemann sum. But there's always a unique output for any x as long as you're within the interval. And of course, what happens if the upper bound is a number that is smaller than the lower bound? Well, there's a property that allows us to swap the bound so that x is always, so that the lower bound is always the smallest number. So if you start with the integral between c and x is the smaller value, you can swap it, no problem. But when you swap bounds, you need to multiply the output by -1. This is where we're finally using that third property that was introduced earlier in this chapter. So let's just construct an example of a surface function with the next example. So let small f of x be defined graphically over the interval -1 to 6. And suppose that big F is the surface function that starts at 0 all the way up to x. So here x is the upper bound. So when we're asking you to compute outputs of big F, it's the definite integral between 0 and x. So we have the graph of small f, and we want to compute outputs of big F. So let's do some examples together to really feel how the surface function big F is constructed on top of the graph of small f. For example, let's compute f at 0. So when you're computing big F at 0, so the input is the upper bound. So we're looking for the definite integral between 0 and 0. So here we go. We're simply on top of a point. So when you're computing the definite integral over a point, this is one of the property. And of course, intuitively, it makes sense. It's just going to be equal to 0. Simply put, in the definition of the surface function, there's always a starting point. And when you're computing the output at that starting point, you're always going to get 0. So now let's do the output. Let's compute the output of big F at 2, which is the definite integral between 0 and 2. So remember, the lower bound is part of the definition of big F, so it's always 0 for that example. And we want to compute the definite integral between 0 and 2. So visually here, we want to use the following areas. So we want first the area, let's say here in green, between 0 and 1, and then this area here in orange between 1 and 2. Remember, for definite integral, those are signed areas, so they are positive if they are above the x-axis, and they are negative if they are below. Here, I already took the liberty to compute all the areas between the graph f of x, small f of x, over the interval minus 1 to 6 by looking at increments of 0.5. So between 0 and 2, I'm going to use plus 0.375 plus 0.125 minus 0.25 and minus 0.75. So if you add all those definite integrals together, you're going to get that the output at 2 is minus 0.5. Now, let's do an example of an output for an x behind 0. Like, for example, let's compute f at minus 1. So the first thing you realize here is that minus 1 is a smaller number compared to the beginning, which is 0 in that definition. So I need to swap my bounds. So I want the definite integral between minus 1 and 0, but I will need to multiply that definite integral by minus 1. So here in darker green, this is what we want. So we know the area is 1, but because we need to multiply it by minus 1, the output is minus 1. So be very careful. Even if that definite integral between minus 1 and 0 is plus 1, because of property 3, we add to multiply it by minus 1. So as an exercise, I'll let you compute outputs for the function big F from minus 1 to 6 by doing little jumps of 0.5. So compute the output at minus 1, which we already did at minus 1, but also try it for minus 0.5, 0 that we did, which is 0, 0.5, 1, etc., all the way up to 6. I have all those outputs computed for you, so make sure you understand where these outputs are coming from. And again, here, just by using basic geometry and using the notion of definite integrals, so sign areas being positive when they're above, negative when they're below, you can compute these outputs very nicely. Now, though, I want to show you what happens when you plot the graph of big F on top of the graph of small f. So we have a table of outputs. Let's plot the points for that big F. Let's draw the graph of that function. So here we go. Let's put all those outputs on the Cartesian plane. So here are the points for big F. Boom. Okay, so I'm looking at the outputs of big F. Now what I'm going to do is I'm just going to connect those points using lines. So here, if you connect those points together, your graph will look like this. So here we go. Boom. Okay, so that's the nice graph for big F. So this is the graph for big F of X. So just using like the good old way, computing outputs, plotting the points, connecting the dot, as if you're just a kid in a coloring book, connecting the dot, hoping that if you follow the numbers correctly, your thing will look like a giraffe. Mine never looked like a giraffe, sadly. As a remark here, one thing that I find interesting to really feel the connection between the function small f and big F, and of course those areas between the graph of small f and the x-axis, is to see like how the function big F changes. And the idea here is that when those areas are above, the function is going up. And when those areas are below, the function is going down. And this is why this is called the accumulation function, because it accumulates those areas. And as long as they're positive, the function will accumulate more and more and will go up. But if those areas are negative, then the function will go down. So here, just to illustrate that, this is not part of graphing the function, but just as a remark. But I drew for you like little arrows, green going up or red going down. And you can see that the function is going up when those definite areas are above, when those areas are above, so when those definite integrals are positive, and you can see that this function is going down when these areas are below, or when those definite integrals are negative. And of course, by how much? Well, they're going up or down by the area. So there's this very nice connection. And this also helps to understand, like, why does the function big F behave in a certain manner especially when you go backward, like before 0, people say, oh, well, the area is 1, but you need to gain 1. So you need to start at -1 and go to 0. So sometimes that helps when you look at these, how these areas will affect how the function is going up or down. Now I want to take the time to describe how big F is behaving compared to how small f is. So here, the first thing I'm going to do is look at how the function is increasing versus decreasing with respect to the sign of small f. So what I mean by this is when you look at the function, big F is increasing from -1 all the way up to 1. And the reason why this function big F is increasing is because the function small f is positive. And then you can see that the function is decreasing from 1 to 3. And the reason why big F is decreasing from 1 to 3 is because the function small f is negative. And then from 3 to 6, the function is increasing forever. Okay, and of course, meanwhile, small f is positive. So while small f is positive, big F is increasing, and while small f is negative, big F is decreasing. And meanwhile, we have a local maximum at 1, and we have a local minimum at 3 on big F, and those corresponds to roots for the function small f. So small f is 0 at 1, and it's 0 at 3, and that corresponds to critical points for the function big F. Now, the next thing that we can look at is concavity. We can see that the function is actually linear between -1 and 0, and the slope of that line is actually 1, which is the value of the constant that is small f. So small f is constantly 1 between -1 and 0. But then the function is concave down from 0 to 2. So the function is concave down from 0 to 2. And that corresponds to what on the function small f? It corresponds to the fact that the function small f is decreasing. So as small f is decreasing, then we can see that this affects the concavity of big F. It's concave down. And then this function small f is increasing from 2 to 4. And that corresponds to the function being now concave up between 2 to 4, the function big F to be concave up between 2 to 4. It's not super obvious, but the function is big F concave down between 4 and 5, and that corresponds to the fact that the function small f is decreasing, and we have two inflection points. We have one at 2, and we have one at 4, and those corresponds to local minimum or local maximum. So we have a local minimum at 2 for small f. It corresponds to an inflection point for big F, and we have a local maximum at 4, which corresponds to an inflection point for big F. So all that just to say that the function big F and small f, they have a relationship. Small f is really acting like the derivative of big F. So like this very important remark here, I took the time to write a star here. So the function small f behaves like the derivative of big F, or in other words, if you compute big F prime, you're going to get small f. Or in other words, that surface function is a primitive for small f. Aha, it is a primitive. So when you construct a surface function on top of a function small f, that surface function is a perfect candidate for a primitive, and that will give birth to the second fundamental theorem of calculus. So here we go. The second fundamental theorem of calculus. If you start with f, small f, a continuous function over an interval ab, and suppose you pick any point inside that interval, then the surface function big F from C to X of small f of t dt is a differentiable function. So there is a derivative, and that derivative, so big F prime, is small f. So in other words, the surface function is a primitive for small f. And this is always true as long as f is continuous. Just like in our previous example, the graph that I gave you for small f was the graph of a continuous function. The surface function that we constructed on top of it was an example of a primitive for that small f. So we know now, thanks to this theorem, we know there's a primitive. We have a green light. We know it's out there. So we can always use, in the worst case scenario, a surface function for small f as a primitive for it. So 2 remarks. I might be repeating myself, but they're very important. So for every continuous functions, those surface functions are examples of primitive. And sometimes, so the second remark here is the interesting one, sometimes the only way you can write down a primitive for a function is by using the notation of a surface function. So sometimes it's the only way. So in most questions, of course, we can find a primitive using basic rules of integration or techniques of integration, but sometimes even if you're a black belt master in techniques of integration, you need to give up and use the surface function notation to construct a primitive for a function. And it always works. So here's 2 examples. So for both examples, we're going to give 2 primitives for these functions. So for small f equal to 6x squared, so we could construct a surface function the following way. We could say that, well, f of x is equal to, so here I'm just going to use the fact that this is an easy function to integrate. So you could use f of x equal to 2x cubed. Oh my God. So that would work. So this would be one nice answer. But you could be creepy and use another way. So you could say, well, if you compute, let's say, the integral between 1 and x of 6t squared dt, so that surface function that computes the area under the function 6t squared works. So it's creepy, but it works. So, and here, make sure you understand what it means visually. So if you have that graph of 6t squares and you start at 1 and you compute the area under from 1 to x, that function that computes the areas, it's like a different notation, but that's actually a function that will be a primitive for 6x squared. So to some extent, you could be lazy now. Every time I'm giving you a function, if I ask you for a primitive, just put it inside an integral, change the x by a t, choose a lower bound that is a number inside the domain, and x is the upper bound. That's it. That's all. You don't need anything. But of course, if there is a way to write explicitly a primitive, I will always expect you to use, okay, the algebraic version for a primitive. But the second example is where things are shining. If you want a primitive for ex over x, so by the way, that function ex over x is defined everywhere but 0, so you have to be very careful. So here, my function f, we will restrict it just for strictly positive values of x. Ex over x, it looks like a very simple function, but if you try basic integration, this is obviously not a basic one. If you try a substitution, this is not a trigonometric integral. This cannot be done using trigonometric substitution. This is obviously not a partial fraction question. If you try to do this by part, it won't work. And actually, if you know every single technique out there, there's no way you can integrate ex over x. It's one of those simple equations that do not have an explicit primitive. But ex over x, because it's defined everywhere but 0, is an example of a continuous function. So we know there's a primitive, but here we have no choice. We need to write it down using a surface function. So here are 2 examples of surface functions. So big F could be the integral between 1 and x of et over t dt. And then another example, the way you change A primitive is just by changing the lower bound. So let's say between 2 and x of et over t. And using surface function, it's the only way. It's really the only way to write examples of primitive, but they work. So those surface functions, those accumulation functions under et over t will be new functions those surface functions will be primitives for my function ex over x. So here, of course, x being bigger than 0 in both cases. All right, but in a nutshell, though, surface functions of continuous functions are always primitives. So if you differentiate those surface functions, you get the smaller function, small f. All right, for that section, that's it. That's all. Bye-bye.